Today, I'm going to introduce our paper, Reliable Decision from Multiple Subtasks Through Threshold Optimization, Content Moderation in the Wild. This is the contents of today's presentation. First, I'll introduce the background and motivation behind our work. These days, there are many abusers who generate harmful contents every day, and social media platforms are struggling to protect users from such contents through content moderation. To effectively moderate harmful content, social media platforms usually use both ML models and human resources at the same time. If the output score from ML model is confident enough, the ML model's decision is trusted. If not, the content is manually reviewed by human moderators. Despite its effectiveness, there exists a problem to consider when operating ML models for moderation. The problem is that moderation policies vary depending on countries and products. A naive solution to this problem is to train and deploy one model per one policy. However, in this case, policy changes require dataset relabeling and model retraining. To solve this issue, many social media platforms adopt multiple subtask approach through third-party moderation services such as AWS Recognition or Hive Moderation. In multiple subtask approach, ML models provide prediction scores of multiple granular subtasks to cover the various moderation policies. For example, an ML model can provide the score for the existence of weapon or pills. By utilizing these scores, social media platforms can easily cope with the changing policies. To make a final moderation decision from the multiple scores, social media platforms usually go through two steps. First, they apply thresholding to the prediction scores to a binary form. Second, they design a decision function that maps binary results to a single moderation decisions. However, it's very hard to find the optimal thresholds because the scores are often not well calibrated. To address this issue, we propose TrustResh, a threshold optimization algorithm that finds the optimal thresholds of multiple subtasks. TrustResh aims to find the optimal thresholds that yield highly reliable decisions in a very efficient way. In the second section, I'll introduce how we formulate our problem setting, including content moderation and multiple subtask approach. The content moderation is commonly defined as classifying whether the given content is harmful or not based on the policy. In an ML-based scenario, the content moderation is defined with the ML model and the corresponding threshold. If the output score for ML model is larger than the threshold, the content is automatically filtered out or skipped. Otherwise, the content is manually reviewed by human moderators. In multiple subtask approach, a set of subtasks S is defined to cover the various moderation scenarios. Here, each subtask S is defined with the subtask-specific model output and the corresponding threshold. To make a moderation decision from the multiple outputs, a decision function is needed. We define O as the output of the multiple subtasks. Then, the decision function D is defined as a function that takes O as an input and outputs the final moderation decision Fx. Here, since every element of O is in a binary form, a decision function can be interpreted as a Boolean expression. This is an example of decision function. Suppose that social media platform for children wants to moderate violent images. Then, the decision function might be designed like this. This was how we formulate multiple subtask approach. From now on, I'll introduce how we set our objectives and define our problem. First, ensuring high precision is very important when determining the threshold, because moderation decisions should be reliable. Wrong decisions might lead to innocent victims or exposure of harmful contents. Also, high recall is important since it lowers the moderation cost by reducing the amount of human labor. From the two objectives, ensure a high level of precision and maximize recall, we can drive the target to maximize. In this work, we target to maximize recall at high precision to reduce the moderation cost while preserving the reliability. This is how we formulate our objectives into constraint optimization. Given the dataset and the decision function, we target to find the optimal thresholds that maximize recall at target precision. Here, each data sample of dataset D, consists of multiple prediction scores Q and the ground truth decision Y. In the following section, I'll describe our threshold optimization method TrustThresh in more detail. TrustThresh involves three main components: score normalization, surrogate gradient learning with truncation, and penalty method. From now on, I'll guide you through these three main components. First, we apply score normalization to get rid of skewness. The motivation comes from the fact that skewness makes gradient-based optimization much harder. Here, normalized score Q hat is defined as the rank of the score divided by the total number of data samples. In addition to score normalization, surrogate gradient learning, SGL, with truncation is the main component of our method. In SGL, the forward pass of thresholding operation is computed as Heaviside step function, while in the backward pass, the gradient is computed as if a differentiable function is used in the forward pass. In our work, we use the derivative of truncated sine function as the surrogate gradient. I'll explain about each pass in more detail. The forward pass consists of two steps. First, we make binary prediction by applying Heaviside step function and decision function. Second, we calculate precision, recall, and loss from the binary predictions and the ground truths. In the backward pass, a surrogate gradient theta is defined to compute the gradients. Using this surrogate gradient is same as approximating the step function as truncated sine function. The idea of truncation comes from the insight that thresholds should only be affected by the scores near the thresholds. By using the truncated sine function, we prevent values far from the threshold from interfering optimization. Here, a learnable parameter W called width controls the range of the truncation. Using the surrogate gradient, the gradient for threshold can be easily computed as this. Similarly, we also update width W as follows. Finally, we design a loss function to effectively target recall at precision. Here, the first term is for maximizing recall, and the second term is for meeting the target precision. Alpha is the hyperparameter that controls the strictness of the constraint. In summary, there are three main components in TrustThresh. First, we apply score normalization to remove the skewness of the scores. Second, we adopt SGL with truncation, where the forward pass is computed as Heaviside step function, and surrogate gradient is used in the backward pass. Finally, we design a loss function to effectively target recall at precision. Now, I will show you the experimental results of TrustThresh. First, we conduct experiments on moderation use cases. We use the dataset UnSmile, which is Korean hate speech dataset that contains labels for 9 hate speech subtasks. We conduct experiments for the two use cases. In the use case 1, a decision function is designed to detect abusiveness. In the use case 2, a decision function is designed to skip harmless content. We use 4 baselines for comparison. First, depth thresh uses the fixed threshold of 0.5. Second, greedy thresh maximizes recall at precision for each subtask respectively. Third, SGL thresh, which is our main competitor, uses SGL, where sigmoid is adopted as a surrogate gradient. Lastly, bespoke is a hard baseline, which is a model trained specifically for the target policy. This is the results of our first experiments. TrustThresh achieves the best recall while successfully meeting the target precision. Dash is used for the case where it fails to meet the target precision. Interestingly, low alpha value tends to yield the better recall. We also conduct experiments on real-world content moderation data. We use the data from the live social discovery platform Azar, which has been downloaded over 500 million times. We compare TrustThresh with SGL thresh and heuristic thresholds set by domain experts. The result shows that TrustResh achieves the best recall over all the target precisions, while SGLSResh fails on high precisions and heuristics shows suboptimal performance. Lastly, we also proved the effectiveness of score normalization by adding it to SGLSResh. The result shows that score normalization improves the performance of SGLSResh, and from this, we believe that score normalization can help any kind of gradient-based threshold optimization algorithm. In the last section, I'll summarize the conclusion of our paper. First, we describe real-world content moderation scenarios based on the multiple subtask approach. We propose TrustResh, a threshold optimization algorithm for multiple subtasks. We hope our system will help those who are operating or will operate ML-based content moderation system. Thank you for your attention.